What's up guys and girls, Raj here, back with another video. A lot of you asked me to compare these three hot technologies right now. So that's what we are going to do in this video. We are going to go over the differences between Lambda, EKS Fargate and ECS Fargate. We will go over different factors, pros, cons, as well as help you choose which one should you use for your projects. But before we get started with the comparison, I need a favor from you guys and girls. Click that like button on the bottom right, smash it. It will take 1 second, it will make you feel great, and this kitten will thank you. Now that's out of the way, let's get started with the video. Let's level set first. So what is AWS Lambda? AWS Lambda is a serverless compute service that lets you run your code without provision or managing any server. Amazon Elastic Kubernetes Service, or Amazon EKS, gives you the flexibility to start, run and scale Kubernetes applications in the AWS cloud or on-premises. And finally, Amazon ECS, or Amazon Elastic Container Service, is a fully managed container orchestration service created and managed by AWS. For ECS and EKS, at the end of the day, the goal is to run your application container. For EKS, that container runs within a pod, and for ECS, that container runs within a task. Now, if we talk about traditional EKS cluster, where the worker nodes are collection of Amazon EC2s, each EC2 can run multiple pods, as shown in the picture. Similarly, for ECS cluster, where the worker nodes are collection of Amazon EC2s, each EC2 can run multiple tasks. In this approach, you are still responsible for managing and maintaining these Amazon EC2s. And you also pay for underutilized or idle EC2s. That's where Fargate comes into play. For Fargate, you do not need to create or maintain any EC2 worker nodes. You simply define your container within a pod or a task, and that pod can run in Fargate. As you can tell in the last diagram, we have a bunch of pods running in one EC2 worker nodes, but here one Fargate can only run one pod or one task. Now that we have the basics covered, let's jump into the differences. Let's start with scaling. Lambda scaling is pretty straightforward. When the Lambda gets invoked, under the hood a microcontainer comes up, loads your Lambda code and executes it. And this process is repeated for all the concurrent executions. So the takeaway is, for each separate concurrent execution, Lambda will simply spin up another instance of the same Lambda code. The two incoming executions at the same time will not share the same microcontainer. As more and more connections come in, more instances with the same Lambda code will come up and execute. Now let's take a look at how Fargate scales. For Fargate, the container is running either within a pod or in a task. When a connection or execution comes in, the CPU and memory goes up a little bit. In this case, I am tracking the CPU. When another concurrent connection comes in, it is not going to spin up another Fargate like it was doing for Lambda. The second concurrent connection still going to the same Fargate executing the application container. But now the CPU for that Fargate goes up a little bit. And let's say another concurrent connection comes in, increasing the CPU over a threshold that you defined. And if the connection keeps on coming, then it will spin up another Fargate. So the main difference between Lambda and Fargate scaling is, for each separate concurrent connection, AWS Lambda will have a separate instance of the function, whereas for Fargate, the concurrent connections may share the same Fargate. Another difference is after the Lambda is done executing, it is gonna shut down. There will be no running AWS Lambda per se if there are no traffic. However, for Fargate, either within a pod or task, the pod or task will keep running and listening for incoming traffic even if there is no traffic at that moment. And this is applicable for microservices running within pod or a task. If you just want to run a short-lived batch job in a pod or in your ECS task, then of course after that batch job is done, your Fargate will shut down. How many pod or task you want to keep on running? That you can define using the pod spec or the task specification file. Which brings us to the scaling controls. How do you scale the Fargate or Lambda? For Lambda, it will scale automatically based on traffic. Since each traffic connection is using its own Lambda instance, there is not much to configure anyway. For EKS Fargate, you need to set up scaling based on Kubernetes constructs, which uses the metric server. So if I go back to the previous slide, as you can see, as the CPU reached a certain threshold, a new Fargate came up with another container running. Using HPA or horizontal pod autoscaling of Kubernetes, you can specify at what percentage of CPU you can scale up the Fargate. Coming back to the scaling controls, similarly for ECS Fargate, you can set up scaling based on CloudWatch metrics, and the most popular metrics are CPU and memory utilization. Moving on, when Lambda and Fargate scale, there is a difference between IP address consumptions. Multiple Lambdas with the same security group and subnet combination share the same IP address. So if the same Lambda is scaling up, even though there are multiple instances of the same Lambda running, they are all reusing a single IP address. So very few IP addresses are used during Lambda scaling. However, for Fargate scaling, each pod or task consumes one IP address. So essentially, one Fargate instance will consume one IP address. So when the same container is scaling, multiple Fargates will come up and it will consume multiple IP addresses. So beware of IP address availability during Fargate scaling. Now let's jump into system integration. This is one of the superpower of AWS Lambda. You can expose AWS Lambda directly out of the box with API gateway and load balancing. Beyond that, Lambda is integrated with SNS, SQS, S3, EventBridge, and hundreds of other AWS services. For example, if you want to trigger a Lambda from SQS queue or SNS bucket, EventBridge rules, it is very straightforward to set up. Also, Lambda runs on public subnet or private subnet or outside a VPC. One thing to keep in mind, Lambda does not give you a IP address. So if you want to access internet from Lambda and your Lambda is in public subnet, since it doesn't have an IP address, even then you need a NAT gateway. Moving on to EKS Fargate, currently out of the box, EKS Fargate integrates with AWS Load Balancer, and EKS Fargate runs only on private subnet. So only way to expose EKS Fargate to the outside world is by using ingress. For ECS Fargate integrates out of the box with Amazon API Gateway and Load Balancer. EKS Fargate can run on public or private subnet, and when EKS Fargate is running on a public subnet, it will give you an IP address, and this can be invoked by the IP address. I actually have a separate video along with demo on how to do this. Check it out if you're interested. Moving on to high availability, for Lambda, under the hood, each Lambda function is deployed in multiple availability zones out of the box. And you do not pay anything extra for this. So Lambda is automatically highly available. And when a traffic comes, it automatically balances the load. You do not need to create a load balancer to split traffic between these multiple availability zone copies of the same Lambda. And even if one availability zone goes down, it will automatically start sending traffic to the availability zone which are up and running. For Fargate, the Fargate is only deployed in one availability zone. If the Fargate goes down, another Fargate will automatically come up. However, there will be a delay. If you want your Fargate to be highly available all the time, you as a user need to deploy the same Fargate into different availability zones. And you do have to pay to spin up the same Fargate into other availability zone. Hence, Fargate is automatically not highly available. Moving on to cold start. So for Lambda, when the Lambda is invoked, the container comes up, then the code is loaded, and then the code is executed. The time it takes for the container to come up and loading the code is termed as cold start. To avoid cold start for Lambda functions for critical time-sensitive APIs, you can use provision concurrency. Provision concurrency will bring up multiple instances of the same Lambda. So in this case, 3 instances of the same Lambda is up and running, and when a traffic comes in, it will use those pre-warmed Lambda instances. So there will be no container to spin up or no loading of the code, so hence no cold start. For EKS and ECS Fargate, the cold start time is defined as when the underlying virtual machine comes up and it starts running the application container. There is no provision concurrency option for EKS and ECS Fargate. If you are using EC2s at the worker node, for EKS you can use over provisioner to reduce any sort of cold start. Another technique with EKS or ECS Fargate is you can keep a minimum number of Fargate running. However, this is not as sophisticated as provision concurrency. Lambda provision concurrency, you can scale up and down, you can do schedule based. It's a little bit more painful to control this with a pod spec or task definition. Without provision concurrency, it is very difficult to tell whether Lambda or Fargate takes more time to start up, because a lot of things depends on the actual code, the application container, what libraries you are installing, etc. So for your actual project, you gotta test it out and measure which has more cold start. Moving on to resource configuration. For AWS Lambda, you can control only memory, and you can configure memory between 128 megabyte up to 10 gigabyte, and the CPU core will be allocated appropriately between 1 to 6 core. For EKS Fargate and ECS Fargate, you can control memory and CPU. However, you have to select from the table. As you can see, if you select one vCPU for the CPU value, you need to choose between 2, 3, 4, 5, 6, 7 or 8 gigabyte of memory. Since for Lambda, you cannot really change anything other than memory, for either memory intensive or CPU intensive workloads, you can only increase the memory. There is no option to keep the memory at a fixed value and just increase the CPU. Whereas, depending on your workload, for EKS and ECS Fargate, you can selectively adjust CPU or memory. Moving on to the basic building block of Lambda and Fargate. For AWS Lambda, you can directly code within Lambda without the knowledge of any container. or you can write your own application container and your Lambda can use that container. This feature is released in re:Invent 2020, and this is actually very attractive to a lot of customers, especially if they're already familiar with container but want to use the system integration superpower of Lambda. I do have a separate video along with detailed step-by-step demo on this. Feel free to check it out if interested. For EKS and ECS Fargate, you have to containerize your application code. There is no option just to run the code without a container. Now moving on to cost. For Lambda, the cost is determined by how much memory you allocate to the Lambda, what is the execution duration for the Lambda, and it is priced per millisecond, and if you have enabled provision concurrency. For Fargate, the cost is based on how much CPU is allocated, how much memory is allocated, and what is the duration of the Fargate. And the duration is priced per second. So if we take an example of 1 million invocations a month, and each execution uses 512 megabytes of memory and 700 milliseconds of execution time, for Lambda, the cost is $6 per month. There is a Lambda calculator for you to calculate the cost. I will give the link in the description, or you can simply Google it. One thing to note is the cost is same irrespective of traffic nature. So if this 1 million times a month is spread out such a way that it is a low number every hour and this number is fixed, or if 500,000 traffic comes within a 30-minute time and the rest is spread out, the cost will be same because each Lambda connection uses a separate Lambda instance. For Fargate, that is not the case. Since one Fargate instance can support multiple concurrent execution, the price will depend on the nature of the traffic. Let's say if the traffic is consistent, stays at a low pace, and one Fargate instance is able to support this 1 million times a month traffic, then the cost will be the cost of the CPU and memory, which comes down to $2.73. If the traffic is scaling up and you need more than one Fargate container, then the cost will increase. It is beneficial for Fargate to have more vCPU and more memory than what's needed for single execution, because ideally you want to avoid a lot of Fargate getting spun up, because you want to avoid unnecessary cold start and IP consumption for the Fargate. When it comes to cost, the cost will depend on multiple factors: nature of the traffic, nature of the workload, as well as scaling criteria. So always do your own cost calculation before deciding whether Lambda will be more expensive or Fargate will be more expensive. There are some other factors. For example, for logging and monitoring, Lambda integrates out of the box with Amazon CloudWatch. Since EKS Fargate is in Kubernetes ecosystem, for logging and monitoring, it requires some installation of some third-party or open source and some AWS agents. For ECS Fargate, it integrates out of the box with CloudWatch. For AWS Lambda, if your Lambda is running within VPC, you can attach security group, which can work as a firewall. Currently, EKS Fargate, you cannot attach a security group to the pod, and ECS Fargate, you can attach security group to the task definition. AWS Lambda has no association with Spot instances. Similarly, EKS Fargate Spot is not supported. However, ECS Fargate can run on Spot, and in those cases, the price will be lower. Another thing, this is not a difference, but something to keep in mind. Sometimes folks will think that Lambda, Fargate, they can only support stateless workload, which is not true. Lambda and Fargate can integrate with Elastic File System or EFS. Hence, if your APIs need to be stateful, you can use any of these. That's not a distinguishing factor. So which one should you guys and girls use for your project? Well, I think you folks got the idea. Depending on the scaling criteria, system integration, cost, resource control, etc., choose the right tool for the right job. Alright guys and girls, that's the video. If you learned something from this video, please click that like button. It really helps the YouTube algorithm. Subscribe and share with your friends and family to help this channel grow so that we can keep learning awesome things together. Alright, I'll see you guys and girls in the next video. Bye.